Free audio post-production by alphonic.com.
We are recording.
The Structural Engineering Podcast.
Welcome back to the Structural... Welcome back to the Structural Engineering Podcast. This week we're talking about collapses, historical collapses. We've got a few to go through with you guys. Each of us dove into to one. Our favorite is that even one that we're attached to in a way. And we want to look at, why does understanding failure matter, right? Failures are the foundation, the progress of our profession. Today, we're diving into some of these collapses that made our codes better and our thinking sharper. Question for you. What is one structural failure that's burned in your brain, and why? Is it something you learned in school? Is it something you heard in the news and you really connected with? Let's see if any of those come up today while we talk about failures. And I have one debate for you. Are modern codes too conservative or not conservative enough? Where do you stand on this? Let us know. I want to make a pitch for our trivia here because we really enjoy putting this together. I'm using it for studying myself, but I think we can all use it to study for the PE, the SE. We're putting out a weekly email, and we just started a trivia on our website as well. You can submit questions if you find something that people get wrong often or something you really like and want to teach other people. This is the way to do it. I'll put a link in the show notes. Check it out and see what your score is. Now on to the first lesson.
All right. For the first failure we're going to discuss today is the Tacoma Narrows Bridge. Do you know where this is, Max, in the country?
I think it's in like the left top.
Left top. You're really close. How about the state of Washington?
Oh, that's kind of left.
So it's located in the Tacoma Narrows Strait of Puget Sound, Washington State. Somewhere I grew up hearing about this bridge many times as a kid, oddly, and then again in engineering school. Is this something you learned in engineering school or in architecture school?
I don't think this really came up. I do think we watched the video of it buckling, but that must have been much younger.
So a big reason why the bridge was put there was it was intended to improve transportation between Tacoma and the Olympic Peninsula. It was there facilitating commerce, commuting, and then military logistics, which we'll get back into, which was really interesting. The economic development by linking these two communities more directly with a bridge was aimed to really grow the region, especially Gig Harbor, if you're familiar with Washington. And another piece of this, as I kind of was alluding to, was a strategic piece of infrastructure. With World War II on the horizon, there's also an interest in strengthening infrastructure for national defense and mobilization.
Interesting.
Yeah, I found that to be, tying the whole state together and being on the West Coast and all of those things going on at that time. So the bridge was completed on July 1st, 1940. It was nicknamed Galloping Gertie due to its vertical oscillations. And that's where I heard about it growing up.
Yep.
It was just a joke that was made constantly or used in conversation or in passing. Something I read about looking into this more was that the contractors, the people building it, nicknamed it that because while they're building it, it was galloping.
Wow.
It was moving. It was twisting. And so think about this. July 1st, 1940, it was completed. November 7th, 1940, just a few months later, it collapsed. So the bridge was not open for very long until it had a traumatic incident. So before we dive into that exactly, let's talk about the bridge construction. So it was a suspension bridge. It spanned like we said, spanned the Tacoma Narrows Strait. The main span was 280 feet at the time. It was the third longest suspension span in the world. The deck design, or the roadway, was supported by plate girders. We'll talk about a little bit more, but this created a solid surface that trapped wind and increased the aerodynamic instability. The deck was unusually narrow for its length. So think about this long, slender road deck. It's just 2 lanes wide, which made it really flexible.
Is the replacement bridge 4 lanes wide, like a modern?
It's a wider bridge for sure.
Okay.
Absolutely. So it's got 2 main cables supporting the deck via vertical, suspension cables, just like you'd think of any suspension bridge, really. And the towers and anchors were structurally sound and survived the collapse, actually.
Hey.
So what do you think went wrong with this, Max, before I tell you what went wrong?
I think it was a wind flutter oscillations.
Really?
Yeah.
You're good. You're right.
I think that's engineering school tells you that.
Yeah, absolutely. So a combination of the narrow deck, solid girders, and minimal stiffness made the bridge vulnerable to torsional oscillations. So from just the standpoint of the structure itself, but then on this day, 3 months after it had opened, a 42-mile-an-hour wind was coming through, and the bridge entered a state of aeroelastic flutter. So it started twisting violently until the deck tore itself apart.
That wind isn't that fast. Is this reaching a harmonic state that it kept propagating its vibration?
Yeah, so let's talk and introduce aeroelastic flutter. And there's kind of a simple explanation to talk about too. So it's a type of unstable, self-excited structural oscillation that occurs when aerodynamic forces interact with a structure's natural vibration modes, extracting energy from the airflow and feeding it back into the motion of the structure. So it's kind of hitting that resonance, and it really creates a big problem. And with many things, but think about bridges, and like I said, solid girders. So the openness of air flying through there wasn't there. It was solid. It was getting stuck. It was pushing, and it was moving it quite a bit. So I think a relatable example to tie this together would be, imagine blowing on a strip of paper and it starts to flap wildly. That's more or less this kind of aeroelastic flutter. And then now you scale that up to a suspension bridge. You run into some problems really quickly. So the collapse was not due to the materials we talked about. It was due to this dynamic instability that really at the time in the 1940s was not well understood. And again, going back to this thought of that wasn't very long ago.
Yeah.
That was 80 years ago. We know people that are 80 years old that were probably alive during this time. I mean, they had to have been.
Good math.
Thank you. So I wanted to stop here, Max, for a second and just get your thoughts about this of like, where, thinking about engineering 80 years ago, what comes to mind? Like, what do these engineers in their office look like?
They're wearing a suit.
Okay.
I'm picturing, I haven't watched this show, but Mad Men.
Okay.
What I have in my
mob
head.
Bosses?
Is that a mob show?
I don't know.
Okay, I don't know. Anyway, picturing people in a tie, suit, a nice wooden desk.
Pocket protector?
Oh, yeah.
Good.
Yeah, you don't want, the pens really run. In that time, the pens.
I really want a pocket protector.
Yeah. Yeah, and you're basically slide rules at this point. I don't think there wasn't a pocket calculator yet. You had some computers that could do it, but it was punch card computers. So you're not using it that much. Although I have heard, we have talked to a guy that mentioning punch card computers in early career and how quickly they could run through calculations was a totally new thing to them and how exciting it was. And now it's so fast. Was the older guy we talked to, he was in
Chicago,
yeah. He was talking about.
I'm pretty sure he was working for SOM. I don't think that guy was from the 40s.
Yeah.
Anyways, that engineer, Max, continuing on that, sits down, was told they need to span this big, straight with a bridge. What are their thoughts? What are they thinking through, and when they're designing, would you guess at that point?
I've actually seen preliminary bridge calcs from the time, not even calcs, sketches of what they could lay out to span this bridge, how far cables will span. And so they had sort of I don't want to say innate knowledge, but they have formed a basis of knowledge on the materials they're using and what they have spanned in the past, what has worked, and how do we lay this into the span we need to do today? Can we put piers there, or does this have to go deep in the ocean? And that's not going to happen. So that's what I'm guessing they started with is pencil and paper.
Yeah, and I think they probably had a good understanding of how gravity works and vertical loads. Maybe started thinking about seismic a little bit, being out in Washington and having some larger earthquakes out there. But when you start thinking about these dynamic effects with our structures, both vertical and horizontal, probably wasn't really a thought at that point. And that's kind of what they found was this was such a new occurrence, right? Most of the bridges they were doing were built up of lattice structures and not solid girders that were so narrow, that spanned so far, so stiffnesses weren't really there. Really drove to this.
I wonder if there is a mentality of flexible can avoid earthquake forces quite a bit more, right? It's pretty clear that when a masonry building cracks and falls down, why it did in a stick frame that just bends in the wind is fine.
Right. So I found this quote, 2 quotes. It said, "Galloping Gertie danced herself to death." And apparently that was a headline of a newspaper at the time.
Interesting paper.
And so that nickname, Galloping Gertie, was coined by construction workers who noticed the bridge was had wild vertical
oscillations?
Oscillations dancing even before it opened.
That's how I dance too, actually.
So the phase became tragically literal on her windy November morning.
Yeah.
So what are some of the key lessons learned here that the engineers listening could really take? And that's aerodynamics matters. Really, as engineers, we learned that bridges aren't just static structures. And it's something that there's so many examples of bridges having, big struggles with vibrations over and over again. There's many failures from that, but also in both like a collapse sense, but like a serviceability, standpoint of this thing just vibrating and people are very uncomfortable with. So, and that's just maybe the human interaction, but there's also all the dynamic aspects of wind that tie into this. From what I saw, a lot more wind tunnel testing kind of came from this, or has since happened.
They realized it was a good idea.
Yeah, it's really become essential. It wasn't standard practice at the time, so dynamic analysis is critical. I think we can all agree on that. Vibration analysis, even our vertical structures, that swaying that building gets into from both wind and seismic is a dynamic analysis, as well as really any vibrations we come across, floor or otherwise. Stiffening things, understanding the stiffness of our elements and bridges and vertical structures, and the redundancy of certain things. There's been other collapses even more recently that of bridges that weren't redundant that really caused an issue. And so I think it comes back to that we're designing smart, simple structures that do have redundancy for something that maybe you didn't think through or didn't expect to happen. A bridge that gets hit by a ship wasn't thought through before, but now it has been. Yeah, that is kind of what I wanted to talk through with the Tacoma Narrows bridge. Luckily, or not luckily, it wasn't multiple levels of complexity of what happened. It's pretty straightforward. And I think as an engineer, it's very logical thinking of how that occurred. The bridge deck wasn't very stiff because it was very narrow, but it spanned fairly far. The girders were plate girders, so it caught the wind really well, and it just unfortunately created that oscillation and fluttering. So
did they, when this fell down and they were going to build another one, I'm sure, imagine what had happened, but did they perform more rigorous testing to make sure?
Great question.
They just built it again. This is the old way.
So I wanted to leave this portion, this example, with just something to think about. So imagine you're the lead structural engineer in 1940, Max. You just watched this footage of the bridge collapsing. And if you haven't watched it, you should look it up on YouTube. It's very interesting. What would you tell your client or the public? So send us a message or leave a comment on this podcast. I think it's another thing that would just be like, what a place to put yourself into. Any initial thoughts, Max?
Oh, absolutely. I looked into a lot of failures, and I think it was such a different time. A lot of these, some building collapses that I looked at, one wall didn't fall down in a 5-story building, and they just used that wall to hold the joist the next time because it was a lot of effort to make a wall. And they had a different level of effort to make a building. They didn't have giant machinery just completely available and thrown up mass timber in a weekend. This took a few years of carrying bricks. So I think they valued things differently and didn't have the ability, didn't have a nice computer.
That's a really good point. All right, Max, on to our next failure we wanted to discuss today. What do you got?
We're going to be talking about Ronan Point. Do you know this one?
I do not. No.
Oh.
I'm excited to learn.
This is a type of building that has had a few collapses. We had one in the U.S., which I can't think of the name of, but I will work on this. It's pushing prefab. So the system they use here is a tower built with large panel systems. They call it this, LPS, large panel system. It's a prefab method with large concrete panels. They're cast off-site and then bolted together. The panels I read were about 6 to 7 inches. I don't know what that really meant, but let's just use the 7-inch number. They were 7 inches thick. Then this thing was assembled on site. This one used the Larson-Nielsen system. It was originally intended for buildings up to 6 stories. This building was a bit taller than that, almost 4 times. It was 22 stories.
Wow.
So they were really pushing the ability of the system and the ability they assumed the system had. This is after World War II, so there's a lot of social changes happening. This is, yours is right before World War II. They needed a lot of housing in England. And so this was a way they thought of, we can produce this very quickly, very cheap, and it didn't work out great for them. There were a lot of issues here. I mean, big issue, it fell down. That's not ideal for buildings. Let's talk about, key design flaws. So there was no structural frame, right? The building lacked continuous structural skeleton. Load-bearing walls were expected to carry the vertical and lateral, no redundancy in the system, just stacked concrete panels to take all of the load out. Many of the connections were friction-based, so panel joints relied heavily on friction, minimal mechanical anchorage. They're pretty vulnerable to separation under any dynamic loading. I saw an analysis of this building after it had some issues, and the building was swaying 6 inches in a wind condition. And so in a 10-year MRI wind, it's usually about 60% of our design wind. So for a everyday style wind, this thing was moving an H over 400, which is pushing the limit for design. I would say far too flexible. And for a rigid style building, right? This is essentially a shear wall building. To move 6 inches in your everyday wind is really excessive.
I would think yes in general, but you think 22 stories? 6 inches?
H over 400 on a normal wind speed? Yeah. I'm going to get out my phone calculator here. So it's 200 feet tall. That would be 2,400 inches. Divide that by 6, what it was swaying. That's exactly 400. Smooth numbers. I mean, just comparing the numbers, and they didn't say what wind speed had occurred when this guy measured this, but, your 10-year MRI wind, I know, is about 66 points, 0.667 of your design wind speed, right? Surprisingly, that is linear. I don't know. But anyway, yeah, and if it was doing that, unless when the guy took the measurement, it was a howling day. This thing was moving the design drift on a normal day. And that was a bit
That
much.
makes sense.
Yeah.
I agree with you there. Yeah.
There was also when I don't want to get ahead of myself here. So why did this thing collapse? How did it collapse? You have any guesses on the structure now, we've kind of described it. What do you think happened here?
I'm going to guess some level of instability occurred with the connections not being very connection-like.
Yeah.
Like you had mentioned, friction-based connections. I would have to imagine something happened to a panel in that it had no redundancy, and hopefully this didn't create... I've already seen the title of it, that the tower collapsed. So obviously has led to a collapse, but some instability of sorts.
Yeah, you're correct. So let me tell you the story here. May 16th, 1968. I'm trying to think of this lady's profession. She got up early, made herself a cup of tea. She went to light her stove. It was a stove her friend had installed for her. There's one that came with the in the apartment. They were mostly pre-furnished, but she had a nice one, and her friend put it in, screwed the gas pipe together. It was all fine. It wouldn't quite spark, so she turned on the gas for a while, lit a match, and bam, it exploded. The wall came down. It pushed the wall out, and there was no redundancy in this building. For 22 stories, everything was stacked on each other, and so she was, I think, on the 19th story, And the 3 above that just came down immediately. Once you took their gravity support out, they were done. And then pretty quickly, the corner of this building just all fell down because they had lost support. Nothing was bracing the floor, and the floor bent out, and then it fell down and pushed the next wall, and down it went, down this building. Luckily, with all these apartments being the same, of course, this wasn't a bedroom. Most people were asleep at this time. This was, I think, the living room, and about half of the living room just went away. So it went the best it could have for life safety. I think 4 were lost. There were a few people that couldn't get out of their bedroom because there was a 100-foot drop outside the door, but it's, kind of everyday stuff. All right, so now you kind of have the story from this, but there are some lessons learned, and they actually did make some changes. This wasn't a 1940s, we'll try again next time. I think this will be good. There were some code changes. We were starting to see codes at this point. We even almost had calculators. So there was a pretty serious regulatory overhaul. UK building regulations were revised, not until 1970, unfortunately, to include disproportionate collapse prevention and structural robustness requirements. This is the same sort of items that are worked into our building code now. We don't really think about them as a standalone basis, but if you think of like column bracing loads, minimum lateral ties for a beam, right? That's 5% of the dead load live load, I'm pretty sure. Like these are structural cohesiveness to keep our structures tied together appropriately. Gas safety reform. So remember, this started with an explosion. The incident led to tighter controls on domestic gas installations. This was the person who lost their wall to start this. And actually, I think she was alive, so I can joke about her. Her friend installed this, and that is leaning to be less of a good idea now. If you're doing your house, I could do it. Send us an email. This extended to a global impact. Ronan Point influenced building codes all across the world, especially regarding redundancy in structural systems, the verification of prefab construction, and ethical responsibility of engineering design. Zach, are there any building code requirements that you could think of that lead to redundancy in design? Or sort of that require redundancy?
When you say redundancy, the thing that always comes to mind is seismic redundancy. And I think it's something that's really important within the seismic world. And really most of the things we design of having a backup piece of it, right? That's the whole idea of redundancy. And I think in seismic, you take a little bit of a hit if you're not redundant. So that's where it always jumps out to me for the most part. Now, there is progressive collapse design of DoD structures when you become 3 stories, which are very complicated designs. And, that all came out of the Oklahoma City bombing. And, that type of structural analysis is quite fascinating. What about you, Max?
I think I immediately think of seismic, but I can't actually picture in a normal building a redundancy case. These are all closer to continuity at this point. TMS, NDS all specify continuous load path for connection. ASC 7, right, has the row of 1-3 for a seismic system that is not redundant, and the progressive collapse comments. But ACI 318 just comments on the integrity of a connection, right? So reinforcing continuing beyond the column beam interaction point. So I didn't find a specific case, but it does lean to the intent in the code. So we do have a couple sections here on robustness, disproportionate collapse, and redundancy. I want to go through a little bit. Some of the things we did take away from this. So the collapse demonstrated that buildings must be designed to withstand localized damage without triggering total failure, right? As we were talking about, this led to the principle of proportional damage. Small incidents, like a little gas explosion, shouldn't cause a widespread collapse. Big ones, yeah, but little ones, no way. Robustness became a core design requirement, ensuring that structures can absorb and redistribute loads, even when part of the system fails.
See, when you're talking about these small gas explosions,
what is the small? All right, anyway,
you leave your oven on for 15 minutes and then you light a match, kind of thing.
I'm a 20-minute oven guy.
That's a big explosion. There's not really anything we designed for that's similar to that. But what I do think of in this is that the basis of structural engineering is positive connection. And I don't think today there is current systems that are designed this way that are, friction based for the most part and not have, some level of rigidity in the connections and that are well tied together. And I think people understand how hinges are created within a system. So I think although our typical residential tower isn't designed for explosion.
Small explosions. Residential tower is always small explosion. You passed PE with that? I had a small explosion question.
How are you defining small explosion?
I don't even know what that means.
I like medium explosion. Well, what else did we learn, Max?
We learned about structural redundancy. Ronan Point lacked any member redundancy, right? If the wall came down, it knocked the wall above it down. The wall was the shear resistance. It was all tied together, which you might argue is efficient. It's also a very bad idea. So engineers began designing systems with alternate load paths, so no single point of failure could compromise the entire structure. We also made some pretty big leaps in connection design, right? So there was a lot of friction connections in this building, but there were threaded connections they just didn't actually put a nut on, or they were standing very tall. So like we had a high anchor rod, and then it was totally deformed down when they assembled this building. When they took this building apart, they inspected each piece. At the time, they would have just blown up a building and thrown it all away. But there were so many issues with this. I don't think it was much later, but they fixed the building. Nobody wanted to move in, believe it or not. And they later, a couple years, I think, disassembled this, and there were a lot of issues. The panels between them was just filled with trash from the construction workers. So it had a lot of silly things going on. And it's kind of my big collapse.
The one thing that comes to mind too that I would take away from this is the really going back to your connection piece is that brittle design is just such a bad thing for us to do. There's brittle materials we utilize, but how do we strengthen them like concrete with rebar and stuff to make them ductile? So that's what goes to my mind as well with this building is that the detailing really allowed no ductility to occur within the system. If thinking through how buildings are detailed today and how there's just, so much more science around concrete buildings and that the connections are ductile and how the beams fail and that you can observe concrete failures prior to catastrophic failures was something that wasn't done at this point or really understood maybe that could have saved a lot of this.
Yeah, if this panel was tied a little more substantially to the rest of the building, it wouldn't have blown away. I think it would have been a easy fix to make this not happen. The building still would not have been in great shape. The drift in a little windstorm indicates that there were some serious issues here. For a panel to just get blown away from a small explosion, whatever that means, but a high air pressure and your entire wall separates from the building, it's not a great design decision. All right, I've got one in my head, and I hear you know a lot more about it than I do, but this is the one that stands out to me as the most significant item that I had learned about in college or before, and a pretty wild collapse. We're talking about Hyatt Regency. What do you got, Zach?
During a Friday night on July 17th, 1981, a dance in the Hotel Grand Atrium was occurring with two suspended walkways, one on the fourth floor and one directly beneath it on the second. It then collapsed onto the crowd below, killing 114 people and injuring 216 people. So this was the Hyatt Regency walkway collapse in Kansas City, Missouri. So the hotel featured a multi-story atrium with walkways suspending from the ceiling, connecting the north and south wings. The original design called for continuous rod hangers to support both walkways from the ceiling. During construction, a design change split the rods into two separate sets, one supporting the fourth floor walkway, which in turn supported the second floor walkway below. This change doubled the load on the fourth floor walkway connections, far exceeding its capacity. And I remember this is like the ethics discussion, I feel like, in college.
This is a shop drawing why you
change.
need to do a pretty solid job reviewing shops, because it can look like a minor change, but it totally changed how the force transfer through this connection. It looks kind of small on paper, and I think if you're not thinking about the force limits, you might say, yeah, that's basically the same. But it's really not. The threads are seeing twice the amount of force. Pretty serious.
I remember the discussion in college that the professor pulled up these two photos before getting into this and asked, what's the difference? And I would say maybe half the class understood that the rod was taking twice the load.
I just want to add a detail, because the rod is not seeing twice the load. The threaded connection is seeing twice the load. The rod was designed to be continuous down to the lower bridge, but it transferred over. So the rod was seeing the same amount, but the threaded connection at that transfer was now hanging the lower bridge, doubling the force on the upper bridge that was transferring over. I don't know. I'll link a photo. It's hard to describe.
So going back to the inexperience of changes, it's really, for anyone listening, I think when you see significant changes coming through, from shop drawings or anything like that, making sure that someone else is also looking at them, you're getting inputs. And that's really, I think, one of the biggest takeaways from this is making sure that, after the design has been reviewed, sealed, sent out, the changes are still being, reviewed after that point. So, So changing this connection, you should, stop right now on the episode and go look this up. Tons of pictures of what this connection change that doubled the load and really became a huge technical issue that led to a failure and unfortunately death. So I think this introduces the ethical implications of the discussion is who approved it? How did communication break down? How has this changed submittal and RFI processes? It'd be very interesting before and after this collapse to understand that from that time. But thinking about our day-to-day work, this is such a simple thing that could be overlooked. I mean, just looking at this detail, if you were to go through shop drawings really quickly or try to, speed up things, I think that to me, a huge lesson and a big part of this is to slow down. In looking deeper into this, there was a lot of fingers being pointed both ways. The fabricator said they had a phone call with the engineer, and the engineer told them it was acceptable and to go with it. And that's why they made the change. And it was very interesting looking that, neither party was taking fault of what occurred. And this is something they obviously didn't catch in construction when they built it, right? It's not seeing these huge dance loads that were occurring.
I think it was also whether it was approved or not. We discussed, put this in a first-year engineering class. Only half people might think it looks wrong, and it could fit people in construction here. I said, this is how it is. This is the design. It is not an incorrect design assumption. It's not like, a concrete column without any rebar. Like, this is a weird design. It looks completely plausible, and it took a dance hall to prove that it wasn't.
So I have a question for you, Max, that I'm just curious what your thoughts are. So if you spot, let's say, a red flag like this, but the PM you're working for just brushes it off, what would you do?
Weird PM management relationship. I think if you see something that's wrong and you're the engineer, that's your problem to fix. And if you are an intern or a 40-year engineer, you're the engineer. So yeah, if the PM says, no, it's fine, say, prove it, and I'll go on with my day, frankly.
Okay.
And I think everyone, I am older than you, but than people listening often, I would not take someone's word on something that you feel like you disagree with. If you have a sense that is incorrect, we do a pretty logic-based math profession here. If you can't prove it with numbers, which you shouldn't always have to do, but if you question it and they say, well, we just think this way, you got to know why. And for your future to know why you should make that decision when it comes to you, it's nice to see some evidence. So I certainly think anyone working with me should ask why I made a decision, whether they are younger than me or older. If you doubt something, ask for an explanation. And if it sounds good, then change your opinion in the future, like how you might make this decision. But
So I think to summarize all three of these failures that we're discussing, the Tacoma Narrows happened due to some dynamics from the wind and the lack of stiffness of the bridge deck, which led to a collapse. I think there's a couple lessons to be learned there. This was occurring during construction, and no one did anything and allowed the bridge to be opened. And so, to me, a big lesson learned here is if you're seeing things during construction, or even after the building opens, it is to your, professional requirements to say something, to fix something, to close that thing, to fix it, because the general public gets access to buildings and roads and bridges with the belief that they're safe because of structural engineers. And that is the most important thing that we do, truly, is the life safety of the public. And if that leads to lawsuits and money, at the end of the day, it really doesn't matter, because you did not, lead someone into an unsafe condition or, unfortunately, potentially kill people. And our second example with the small explosion in the building, I think the big takeaway there is stability, positive connections, ductile detailing of connections, and how things go together. I mean, the system sounded like some loose Lincoln logs that with just a small push would collapse it. So I think, thinking through how we detail our buildings and just general stability, thinking through on every structure you're working on, just those nuances of things that could occur. And I think today's detailing of concrete buildings and steel buildings have really led to a more robust structure. And then the last one here, the Hyatt Regency failure, is to slow down and really pay attention to the connections. Both, I mean, Max, this could have easily occurred during the design documents and maybe overseen, but was a change in the construction shop drawings, and someone overlooked or kept moving, and something that could so easily happen to anybody if they just were moving a little too quickly. So to me, those were kind of the three big lessons I took out of those. What do you think, Max?
Ooh, I don't think I have a takeaway that sums them all together. Certainly take your time in thinking about decisions before you review a shop that is different than you designed, but it looks good enough. So like, why is it different? What are you seeing here? I think the other two collapses, I think Ronan Point is pretty shoddy construction in modern standards. It does not look nearly good. Tacoma Narrows, we were learning about wind design. So it was a bit, that is harder. Like, there's no blame on that one. It's just that's sort of a natural phenomenon that we didn't quite understand yet. So I don't know. I don't have a solid takeaway that applies to all of them. Do your job better is a nice one. But they all have different components that were done poorly, and most of that has been picked up. We are still not exactly looking at every shop drawing correctly. The recent failures, Hard Rock Hotel, that is a shop drawing. So we still have a tendency to just review shops quickly. I always shake myself out of this, but we'll be like, that looks like the drawing I gave. Take a moment. If there's any differences, know why. And you can't know if there's a difference unless you look at each piece. So that is my personal takeaway. It doesn't link it like.
So Max, on top of this, something I thought was important to talk about is maybe some current trends that I've read about or I've seen. One is material shortages, definitely through COVID, this leading to substitutions. What I thought of this was that with substitutions, maybe there's quick review or quick changes and not maybe always fully understanding what those changes could do to your design. So I think, again, slowing down, understanding what you're changing and why is very important, just like the Hyatt Regency. Value engineering, cutting essential redundancy out of what we're doing. Another time where there's a lot of pressure of money and schedule to get things pushed through. And, I think as structural engineers, we have to push back pretty hard quite often to make sure that our designs are safe and what we're doing makes sense. And then the last one here, I really wanted to talk to you about and get your input on is the unneeded complexities in design and code. Are engineers adding complexities that are not needed? Are they not pushing back hard enough on architects to make their buildings, more simpler? And, simplicity is very important in what we do because we know simple things have worked and have worked many times. Doing something for the first time ever is not always the best thing. So I think driving our designs to not be complex is an important thing for majority of the engineering world. What are your thoughts?
I think being able to capture unique buildings in a codified sense is pretty powerful, and we're heading towards that with a bigger code. Like our codes continue to grow, and in a lot of cases, that can be used well. But for a simple building, our 2-story rectangles, it might be pushing a little too complex. And there are also people pushing for a simpler version of a code, a break-off code for these more fundamental buildings that just has straightforward procedure. All right. I don't know anything about this actually, but the seismic, and I have a feeling you won't either. In the seismic section, right, there's the typical base shear calculations, period of the building, and there's also a simplified method later in this chapter, which I have flipped through once a few years ago, but never used. Have you ever used this?
No.
Yeah.
I've seen it many times.
Yeah. There are certainly buildings that this makes the most sense. And I think that style is how I would like to see the code broken down into, like, here's the math you can use for unique buildings. And then here's the baseline for something that's simple. You don't need to think about the period of your 2-story house. Like it's fine. And so breaking those apart a little bit better, I would like.
Something that has always stuck with me that I struggle to think that we've made it better, and I would really love to get input from our audience on this, is that with the UBC, there's just a constant pressure throughout the vertical height of your building for the most part. Let's say it was 35 PSF, and every building was designed for roughly that same value. I think we've added too much complexity into the way we design buildings with wind and come up with those values that could lead to actual problems. We're not going back and retrofitting buildings for wind of these buildings that were done with the UBC or with constant pressures, but yet we've decided that we needed to do more or needed more values. And I think creating a simplified code for probably almost 90% of buildings that are built a year would be really important to making sure that we're keeping things simple just from a loading aspect. I mean, sometimes when you get into the analysis of the actual materials, it gets complex. But it feels like getting our wind load should be really simple.
There is an argument that are you being too conservative and your building costs more than it needs to, and you have double the shear wall because you're applying 30 PSF uniform. So yeah, there is an argument the other direction, and I don't know what the baseline is. In my shear wall example right here is like, well, if you had a house and you did if you used the UBC for a house today, and I think it was a regional, but if we were using a 30 PSF uniform everywhere, and then we used AC7 and we saw that it was 24, and it adjusts as you go up the building, maybe we have to put unnecessary 5 foot on each side of shear wall. Depending on the structure, will that really affect the cost? And most houses have all shear wall anyway, so it's fine. Yeah,
I think it'd be a very interesting analysis and white paper to write to figure that out, because to the best of my knowledge, it wasn't changed because of cost. It was changed because we had better data.
Yeah.
And not saying we should be conservative in everything we do and just have tons of conservative built on itself, but having a couple more feet of shear wall on a building or a house doesn't feel like it's ridiculous. Double the shear wall, sure. I don't know if it necessarily led to that, but I think just putting myself maybe in the shoes of that engineer of engineers 30 years ago that got to just use one wind pressure, they weren't sitting there guessing if they applied the wind pressure correctly. They used the right one. They just had a wind pressure. And now you need, sure, you can do it by hand. I'm sure most people listening use some level of a spreadsheet or a program to get their wind pressures. And I think if we have to consistently lean on programs and spreadsheets and just be able to get the simple loads to our buildings. It seems like that's a failure in design and just like how we're doing things in general. It just seems overcomplicated for no good reason.
Yeah, I don't know my final takeaway, which one or the other, my final opinion here, but it is a little conservative, uniform on everything. We have improved for many reasons, data available, computational ability, but is it that much better in many cases? Would it change most structures? Probably not. For a 5-story? Yeah, certainly. For a 2? No.
And to me, the one place of the code that I have no problem with changes and a little complexity to is earthquakes. The seismic section, earthquakes are really complex on how buildings act and move and fail versus our wind loads, right? You're not seeing buildings failing due to wind.
Even with earthquakes, we are taking a fundamental look at the loads. Like the loads that we apply are not the loads the building sees. They are reduced many times from the acceleration of the earth and then the yielding based on a factor that we have generated on the strength and ductility of the system, how much yielding occurs. Like we're taking movement of the earth that we can't predict that well and dulling it down, saying the building is going to fail. And if we track the load this way, we're tracking an appropriate level of load. We can definitely do better, but even that one is so simplified.
So to close us out here, I think every failure is an opportunity to learn and to make us better as engineers and as people. And I would encourage all of our listeners to keep asking questions, getting their designs reviewed, and especially speaking up when they see things that don't look right or that they believe are wrong. So I'd encourage all of you to share this episode with your junior engineers, your EITs, even your licensed engineers or project managers. Just it's a good time to remember that, you know, these failures did occur and we have learned a lot from them and what those lessons were. And as we started the episode, definitely send us what your favorite story is of what you've learned from failures, either in history or maybe one personally, and we'll highlight those in upcoming episodes.
I got a trivia for you to end this episode. We're talking about calculations. I'm sure you've heard of Excel. You probably use it a couple times a day.
What's Excel?
That's pretty fundamental to calculations. Like every company has in-house spreadsheets that does a lot of these calculations Excel based. When do you think Excel was invented? Invented is the wrong word here. It had a bit of a history, but when did Excel that?
I'm just going to say 1997. I know that's going to be too late.
That's a good, yeah. It's a good year. 1985.
Okay, I wasn't too.
1979 is when Excel style thing was developed, but 85 is Excel.
I'm looking up. I heard this a while ago. What do you think the percentage of Excel spreadsheets contain errors?
90.
Yeah.
Is it really?
Yeah. So going back to my thought about keeping things simple is just think about that. Like you mentioned, every firm has in-house spreadsheets. The likeliness that there is an error in that spreadsheet is very high.
Yeah.
We'll leave you with that. Thank you for joining this week's episode of the Structural Engineering Podcast. Reach out to us however you'd like. We'd love to hear from you on both this episode, but future ones that you'd like to hear, along with guests. We love when you guys connect us with people and want to have them on the episode. So have a good one.
See ya.
Free audio post-production by alphonic.com.